As Brian mentioned, I'm Brandon Alexander, and I'm a web robotics engineer at Willow Garage. And today, I would like to show you all how you can get your robots on the web. But before we get to that, let's go all the way back to RosCon 2012, when Ben Pitzer, on Sarah Ostentowski's behalf, gave a presentation on web-enabled robotics. Back then, the state of the art was the original RosJS, RosBridge 1.0, and WViz, an RViz-like replacement for the web. So although only a year ago, before that, the two big players was Bosch and Brown University. But although only a year ago, we have learned a lot. Web technologies and web performance has increased at a dramatic rate. So a group of us got together to set out to design the next group of web tools for robots. And we set some goals. We wanted things to be modular. If you want to add a 2D map or a 3D rendering of your robot, you should be able to plug in just that component. We wanted to adhere to the web's best practices. So that includes things like emitting events and using callbacks in JavaScript, as well as using HTML5 technologies like WebGL, WebSockets, and the video plugin. We needed things to be robust. So we added unit test, we've added Travis CI integration, and we do code review by GitHub pull request. But most importantly, we wanted this to be about us. We wanted this to be about the community. So with that, the community grew from Bosch and Brown University to include Eugen Robot, Willow Garage, and WPI. And we named our group. We named our group Robot Web Tools. And this is a screenshot of our site that we just launched this week. I highly recommend taking a look after the presentation. It has tools, demos, documentation. And here's the tools we've created. We rewrote RosBridge from the ground up to be more robust, more performant, and to adhere to a well-defined protocol. We wrote RosLibJS, which exposes the core functionality of ROS to the browser. And we wrote ROS2D and ROS3D.js. But enough history. The point of this presentation is to show you all how you can get your robot on the web. Now, I realize there's a wide range of backgrounds here, from Python to C++ to Android developers. But my goal is for all of you to be able to go home after this and be able to add a web interface to your robot. So to get started, all you need to do is to get started, you just need to write some HTML. And you can do this on any platform, Linux, Mac, Windows. And using your favorite text editor, you just have a basic HTML template, head, body tags, and some text to make it look attractive. You don't need to install something like Apache to get started. If you already have Python installed, you can just cd to the current directory, type python-m, simple HTTP server, and you're ready to go. I'm actually running that command on this computer right now. And to try it out, bam, we went to localhost 8000, which is the default port that Python's simple HTTP server provides, and we typed in the HTML file's name. But how do we get this computer and a web page running on this computer to talk to a robot somewhere else? And that's where RosBridge comes into play. RosBridge creates a WebSocket connection between your browser and your server. What that means is that WebSockets provide a bidirectional, low-latency communication between your browser and your server. So it opens up the connection, it takes in a JSON message, and then it converts that JSON message into a ROS call. And the same works in reverse. So if your web page is subscribing to a topic, it sends a JSON request to RosBridge over the WebSocket, and then RosBridge creates a new node that subscribes to that topic, and then when Ros publishes a topic, it goes to RosBridge, converts to JSON, passes it back up over WebSocket to the browser. It's apt-gettable. You can just do sudo apt-get install rosgroovy, RosBridge suite. And it also has a nice, convenient ROS launch file. So right now, I'm running RosBridge on a Turtlebot 2 at Willow Garage's offices in California. So let's get this web page that you just saw on this computer to talk to the Turtlebot 2 halfway across the world, hopefully. And that's where RosLibJS comes in. RosLibJS it exposes the core functionality of ROS to your browser. What that means is that you have a nice API in JavaScript for things like service calls, publishing and subscribing to topics, TF subscriptions, ActionLib calls, and so forth. So we include the library, and then we create a ROS object, and we give it the URL of the WebSocket connection on the Turtlebot 2. And to try that out, it should eventually connect to the RosBridge running on the robot, assuming I set up my VPN correctly, which I'm afraid I did not. That is okay. I did not expect demos to work live and dealing with robots, so I have a video backup of everything. So that green text is what I was looking for in the other window, and what this shows is that it's successfully connected to RosBridge. All right, so we can now connect, or in theory we should connect from our computer to a robot somewhere else. But how do we get data from it? Just like in RosPy or RosCPP, you're able to subscribe, you create a subscriber. So in this case, we subscribe to the robot pose topic, and we give it the message type. And then we just call subscribe. What happens here is when we call subscribe, RosLibJS sends a JSON encoded message to RosBridge saying, hey, can you subscribe to the robot pose? At that point, RosBridge spawns a new node that's subscribing to /robot pose. Then whenever Ros publishes that topic, the node receives the message, RosBridge then takes it, JSON encodes it, passes it up to the web page, at which point this callback function is called with the pose object. And here's a video of that. So we've connected to the robot, and we're receiving the robot pose. We just apply some nice formatting, and we insert it into the HTML inside the callback function. But just text of a pose doesn't mean a lot without a map. And that's where ROS2D.js comes in. ROS2D.js provides a 2D scene graph for your browser with some additional ROS functionality. So what that means, you create your root scene, your root 2D scene, and you give it some basic coordinates and where it should be on your web page. We then need to add components to this scene graph. So ROS2D comes with occupancy grid client built in, which means that by calling this function and giving it the root scene, it will subscribe to an occupancy grid topic, bring it in, parse the message, which is just a bunch of zeros and ones, and then convert it into and render it as a 2D PNG image. Now, occupancy grid is a gigantic message. So it takes a little while to load, even when I was running this locally. So we've connected to ROS, we've now subscribed to the map, we've received the giant message, parsed it, and then rendered it. And this is the floor plan of Willow Garage. So we're already getting the pose information, and we can render 2D scenes like we've shown in the map. Let's add the pose to that. So we'll create a basic triangle to reflect the robot's pose, which is also built into ROS2D. We give it some dimensions, we tell it to pulse and so forth. And then in the subscribe function you saw earlier, where we print it out into a table, we just take that pose information and we set it into the robot's marker's position and orientation. Then we just add it to the scene. So in roughly 15, 20 lines of JavaScript, we were able to bring in a map, render it to the browser, and then eventually be able to display the robot's pose and its orientation and everything in the map. But some things require more than just viewing things in 2D. Some things in robotics require 3D viewing. And that's where, as you probably have guessed, ROS3D.js comes into play. ROS3D.js is similar to ROS2D.js in that it provides a 3D scene graph with some additional ROS functionality for the browser. It's built on the incredibly popular 3JS library, and it uses the GPU and WebGL in the browser. So just like in ROS2D.js, the first thing we need to do for ROS3D is create a basic scene node. So the root scene node, we give it where it should go on the web page and the coordinates of what it should do. And in our example, let's render our Turtlebot 2 in the browser, in 3D. So we create a TF client. We give it a threshold and a throttling rate. And then the juicy part is the URDF client. URDF client, we specify the TF subscriber, we specify the resource URL of where it can find the collada file of the Turtlebot, and then we tell it the scene which it should add itself to. URDF client is then responsible for subscribing or fetching the Turtlebot 2's URDF, taking all the mesh files needed, and then rendering it in the browser with no plugins in 3D. So as you can see here, we still have our 2D map on the right that's subscribing to the occupancy grid, getting the robot's pose, and now we've rendered a nice looking Turtlebot 2. We can move it around, pan, zoom, rotate, and so forth. And this is the same URDF, by the way, that you would use in something like RViz. And the same mesh files, too. So we're already getting an occupancy grid and displaying it in 2D, and we already have the robot's pose. So we can actually take the same, get an occupancy grid using ROS3D's occupancy grid client, render it in 3D, and then add the robot, the robot model to that location. So in roughly 5 lines of JavaScript, we can now add the robot, the URDF model of the robot, render it in 3D at the exact pose it should be, which will take just a second. And there you go. So you can see the same map displayed in 2D with the triangle pose, as well as the Turtlebot 2 displayed in 3D with a nice 3D occupancy grid. But to really hit home the point that you can just add the components that you need, let's add one more feature for our final example. Let's add the 3D floor plan of Willow Garage to our demo. So the first thing we do is just create a mesh resource. This is where we specify the collada file of Willow Garage's floor plan. So it includes the walls, windows, and so forth. We then create a scene node, which we give it the mesh information. We give it an offset pose of where it should be on the map. And then we just add the object to the scene. So in roughly, 10 lines of JavaScript, we're able to add a completely custom 3D component to our scene in the browser. That can be viewable on any platform. And that's really what I want to hit home during this presentation. You can add components. You can add any components you need or create your own and render them and use them in the browser and make them accessible not just on someone running Ubuntu, but someone running a Mac, Windows, even some versions of the newer Android phones. And we hope that people do start creating widgets and do start creating components. The whole point of this is to be about the community. And people already have started doing this. So a lot of the 2D stuff you saw with getting occupancy grid, displaying the robot's pose, and so forth, one person already wrote nav2d.js, which wraps all of that, which is already fairly simple, and made it just a couple function calls to add 2D navigation to your robot in the browser. People are writing entire systems and applications with this too. For example, Russell Torres at WPI used these components to write the robot management system. He did that in order to perform robot studies for his PhD work, online. He found out an easier way to be able to get extra participants. So what's next? Well, one thing I didn't actually have a chance to show that's in there today in ROS3D.js is interactive marker support. So the same interactive markers you're used to on things like, with things like in RViz, you can now use in the browser. But you'll also notice this black display in front of the robot. That's a sneak peek at an upcoming feature worked on by Julius Cameron at Willow Garage on being able to stream depth cloud data from your robot and render it in the 3D scene in the browser. And although it's not displayed in this example, it will include the RGB data as well. If you're more interested more on that particular feature, I believe he's going to put a blog post on Willow Garage's website in the near future. And you can also, as you can see, right-click, select, target point, and so forth. So a lot of people have put effort into getting robot web tools launched and getting the tools created. But I'd like to give a special thanks to Russell Torres, who's now the community manager of Robot Web Tools. He's put a tremendous amount of effort during his time interning at Willow Garage and Bosch to get ROSLib, ROS2D, and ROS3D.js out the window, launching the website and adding tons of documentation. I'd also like to thank Jihoon, who's giving a presentation later today. Jihoon has been critical on getting ROSBridge patched, updated, released, as well as doing the same for things like the different components, the different core libraries, and different widgets. And then finally, I'd like to thank David Gasso. David Gasso wrote the original interactive marker implementation. And now while he's at Willow Garage, he ported that functionality into JavaScript. What I think is really exciting about that is David is not a web developer. He has his own opinions on JavaScript. But he was able to take his knowledge in C++ and OpenGL and port them over to JavaScript with amazing results. So if you would like to know more I highly recommend taking a look at robotwebtools.org to get a list of what's available, what tools are out there, and to see live demos from the browser. And then later today, I'll be putting these slides up online, and I'll tweet the address for that. And if all the code for this, if you want to run it on your own robot, is available on my GitHub account, along with documentation on how to run it and plenty of comments. And that's it for me.